Hello, my name is Hunter Gibson, and this is Project 1.6, my ISP, the weather station. First off, the main theory behind the circuit. The weather station combines sensors with a microcontroller to measure and display environmental conditions. The AH10 sensor is used to measure temperature and humidity, using its built-in thermistor and capacitive humidity sensor. Data from the sensor is processed by the 18-mega 328P microcontroller on the Arduino Nano, which communicates with the sensor via I2C. The processed data is then displayed on an SSD 1306 OLED screen, which provides a clear and visually appealing interface. The AH10 is an integrated digital sensor designed to capture temperature and humidity data by outputting digital values using I2C. The chip uses a 3.3 volt regulator, a 10K resistor network, a level shifter, and an I2C address select to take data from the sensor to I2C communication. Next, the Arduino Nano is a compact microcontroller board based on the 18-mega 328P or 18-mega 168 designed for the embedded project. It operates at 5 volts, features 14 digital I/O pins, 8 analog pins, and supports USB Mini-B for programming and power. In this project, the Nano acts as the central microcontroller, taking the reading of data from the AH10 sensor and displaying this data on the SSD 1306 OLED display. The purpose of this circuit is to accurately read temperature and humidity. These measurements are fundamental in weather prediction. Temperature influences air pressure and wind patterns, while humidity affects precipitation and visibility. By providing real-time data on these variables, the weather station helps users identify changes in the weather. For instance, a sudden drop in temperature and an increase in humidity could indicate an approaching storm. Similarly, consistent high temperatures and low humidity levels might suggest dry weather or potential drought conditions. And finally, a description of the code used. The project begins by including essential libraries that facilitate communication with the AH10 sensor and OLED display via the I2C protocol. These libraries provide pre-written functions, simplifying interactions with the hardware components. In the setup function, the code initializes serial communication for debugging and verifying the system's operation. It then attempts to initialize the AH10 sensor. If the sensor is not detected, the program enters an infinite loop to signal an error. Upon successful initialization, the code retrieves the print's detailed information about the temperature and humidity sensors, ensuring they function correctly. The OLED display is initialized with a specific I2C address, displaying a brief splash screen before occurring it to prepare new data. In the main loop, the program continuously reads the current temperature and humidity data from the AH10 sensor. It prints this data to the serial monitor for real-time feedback, which is very useful for debugging and verification, as I soon to find out. The OLED display is updated by clearing its buffer, setting text properties such as size and color, positioning the cursor, and printing the temperature and humidity readings. This ensures the information is current and readable. A short delay between data readings provides a smoother refresh rate and prevents overloading the I2C communication. All in all, of all the projects we did this year, this is my favorite. I found that thinking, visualizing, and actually doing your own project and being given the responsibility to choose what interests you in digital technology was something that I don't get in any other course, and I'm truly grateful for that opportunity given to me.